Hello everyone, welcome to Bihari Academy. This is Dr. Rekha Piliadula, researcher by profession. Today we are going to discuss about different types of coordinate systems that are very useful in dealing with many problems in electromagnetic theory. We have two types of coordinate systems, linear and non-linear. The linear coordinate systems, they are useful in explaining or defining and describing a system through a linear transformation or linear dynamics within the space of three coordinate system. And the nonlinear or curvilinear coordinates, they are useful in defining and describing a system which is involving more complex transformations or dynamics like rotations, etc. So what are we waiting for? Let us start the discussion. So now we are going to see different types of coordinate systems that are available. So as I already told, we have linear and nonlinear coordinate systems. So if you check, the linear coordinate systems are also known as rectangular coordinate system in three-dimensional space. And coming to the nonlinear, these are also called as curvilinear coordinate systems. In nonlinear coordinate systems, we have two types. One is cylindrical coordinate system and the other one is spherical coordinate system. This is also called spherical polar coordinate system. In this, what we are going to see is, we are going to study the relationship between linear and cylindrical coordinate system and the relationship between linear and spherical coordinate systems. And in third step, we are going to see the relationship between both nonlinear coordinate systems, that is cylindrical and spherical coordinate systems. So now let us see the relationship between rectangular coordinates and cylindrical coordinates. Here, rectangular coordinates are x, y, and z directions. Any point that is defined in this three-dimensional space can be defined with three straightforward coordinates or linear coordinates. Say, for example, we have a point Q here, which can be defined as x, y, and z as its coordinates. That means the point has started its journey from the origin and it has traveled to a distance x along x direction, and it started traveling along y direction, and then it started traveling along z direction and landed over here. So that is how you arrive at this point Q. And what is cylindrical coordinates? If you have a same kind of point Q here in the cylindrical coordinate system, if you have a point Q in cylindrical coordinate system, then you can define this point, data point, as its position or from the origin, and the angle theta it made with respect to the x-axis and the z coordinate. Then it traveled along z-axis, so it landed over here. That's how you can define a data point Q in this three-dimensional space of cylindrical coordinate system. So now, how we can define this r, theta, and z? Say this is r, which is making an angle This is Z coordinate. It has traveled a distance y along y direction, and here is the this is x. So now if you make this as the triangle, how you can write? The angle between the x and y is 90 degrees because this angle is 90 degrees, right? So now if you suppose that x is forming base of the right angle triangle and y is the opposite side, and the angle between x and y is 90 degrees, and here is the r. This is the angle theta, that r is deviating from x direction. Now, as per the Pythagoras law of right angle triangle, you can write r is equal to square root of x square plus y square. And how you can define theta? If you take tan theta, it will be opposite side by adjacent side, that is y divided by x. If you want to find out theta, you can do the tan inverse. So now our aim is to write rectangular coordinates. We can take them as old coordinates. We are going to define old coordinates as function of new coordinates. Here new coordinates are cylindrical coordinates. Let us try to write that. That means left side we will be having x, y and z, and right side we should define x, y and z in terms of the new cylindrical coordinates. That means we should have r, theta and z. Let us try to do that now. Here if you consider this triangle, if you take cos theta, how you can write cos theta? Cos theta is adjacent side by hypotenuse. That is adjacent side is x here, hypotenuse is r. And if you write sin theta, opposite side y divided by hypotenuse r. How you can write x from here? X is equal to r cos theta. And from here you can write y. Y becomes r sin theta. And what is the other coordinates? Z. Here z is same in both the coordinate systems, so there will be no change in z, so that z becomes z. So now if we summarize the relationships between the rectangular coordinates and the cylindrical coordinates, you can write x is equal to r cos theta, y is equal to r sin theta, and z as z. So now let us see the discussion in order to form the relationship between rectangular and spherical polar coordinates. So as we already have seen rectangular coordinates, they are x, y and z. How you can define a same point q in three-dimensional spherical polar coordinate system? We have seen in cylindrical coordinate system that one of the coordinates is r, and which can be represented like this in xy plane. This can be represented as r having a rotation theta through an angle theta from with respect to x-axis, and this is the second coordinate in cylindrical coordinate system. Spherical polar coordinates, we have another coordinate called rho, which is the position coordinate in three-dimensional space. R is the position, the magnitude of the position vector of a point in two-dimensional space, but rho is the magnitude of position of a point in three-dimensional space. And another coordinate is theta, and the last one is phi. In excess to the position and the angle theta, this angle, and phi is the polar angle. If we define the position of point Q in three-dimensional space as rho, like this, phi is the angle that this position vector is making with respect to the z direction. This is phi. As rho is the position, magnitude of the position vector of a point Q in three-dimensional space, we can write it as rho is equal to square root of x square plus y square plus z square. Say for example, this is x and this is y, and this is z. Always we should remember that r and rho are not equal. R is the position, magnitude of the position vector in two-dimensional space, whereas rho is the distance of a point in three-dimensional space from its origin. So rho is related to the three-dimensional representation, r is only in a plane, like in two-dimensional representation. So we already have seen how we can dissociate r with respect to x and y. We have x is equal to r cos theta, y is equal to r sin theta. And now our aim is to represent the rectangular coordinates x, y, z in terms of as a function of the new coordinate system of spherical polar coordinates rho, theta, and phi. So we have to define x, y, z in terms of rho, theta, and phi. Let us see how we can do it. If you observe this geometry, we have to notice that the angle between this r and z is 90 degrees. As they are having a perpendicular angle between them, we can form a right angle triangle having r, z, and rho. How can we do that? Let us form a triangle, right angle triangle, with r as the base, z as another z, and this is the z axis, this is rho, and the angle between z axis and rho is phi. As alternative angles are same along the straight line, both the angles are same. Now let us write cos phi and sin phi from this right angle triangle. Cos phi is z by rho and sin phi will become r by rho. Now from this we can write the value of z. How we can write z is r cos phi and r will become rho sin phi. So now let us replace r as rho sin phi in the expressions of x and y. So now x will become rho sin phi cos theta and y will become rho sin phi sin theta. And z is rho cos phi. So this is how we obtained the relationships between rectangular coordinates and spherical polar coordinates. Now let us summarize x, y, and z. And before that we can write cos phi as z by rho, and cos phi will become z by square root of x square plus y square plus z square by replacing the rho value. And now let us write an expression to relate the theta value. For that we have to divide 2 and 1 so that we can obtain tan theta as y by x. And to obtain that theta we have to do inverse tangent, Now these are the expressions that we have obtained out from all the derivations. Now let us summarize x, y, z in terms of rho, phi and theta. So now let me write the relationships altogether that we have obtained between rectangular and cylindrical coordinates and rectangular and spherical coordinates. Here x, y, z are the rectangular coordinates, or theta, z are the cylindrical, and rho, theta, phi are the spherical coordinates. Here, the important things that we have to remember while dealing with these coordinate transformations are r value lies between minus infinity to plus infinity, theta value lies between 0 to 2 pi, and rho value should always be positive so that it is always greater than or equal to 0, and theta value lies between 0 to 2 pi, and phi value extends from 0 to pi. So that's all, and here are all the expressions we needed, and in next video